Well, let's work a few problems on the board here first, maybe, and see what we've got, and then we'll do the sample test 4. I know a lot of you have already been looking at that. So let's see here. We have, 2-methylbutane, and we're chlorinating it. The arrow shows molecular chlorine, Cl2, and what's H nu again? Light. So we're shining light on it, initiating as a radical reaction. And this implies one equivalent here, but remember, chlorine is not very selective. So we're going to get a variety of monochloro products. We'll get that one. The 2 methyls on the isopropyl fragment are the same, so that's one. And then we'll get this tertiary structural isomer, and then we'll get secondary chloride. And we'll also get the methyl on the end is distinct. I think that's 4 possible structural isomers. I can't see any more. And remember, this one does have a stereocenter, so that has 2 stereoisomers, the R and the S form. So if you counted up the total number of isomers, I'd say 5. Structural isomers, I'd say 4. Okay, so can be a little more clear there. But that's just with one equivalent of chlorine, you'll get a mix of these. Remember we said you don't need to be able to tell which one's major or minor. Just show the mixture. In contrast, bromination of the same substrate will give high selectivity for what? The highly substituted bromine. And that's because the propagation step is, the first one there is endothermic. So that lets the systems differentiate very clearly between the tertiary position or a secondary or primary position. It's 1,000 times more reactive for the more substituted spots. So that's the only one you need to put there. And I just say there's one isomeric product. When we've done these type of reactions, I can verify bromine is very selective that way. Now, here's a little bit of a twist. We've got a chiral alkane here, this stereocenter. It's kind of an artificial one. A propyl, ethyl, and a methyl. There's a hydrogen going back there. I think that's the R in enantiomer. If you do bromination of that, look, what will we get? We'll get, again, the more substituted bromide. But what happens to our stereocenter? It becomes a mix now. It becomes racemic, equal amounts of DL. And why is that? Because the intermediate radical is what? Flat. And so you can attack either top or bottom. Remember, it's sp2 hybridized, so it'll be trigonal planar radical either from the top or the bottom for the last propagation step, and that will give the racemic in that case. So a little bit of twist on those couple of reactions. We're starting out with 15 here, the more fresh reactions. And here we got similar substrate. How many total isomeric chlorides will we get? Well, we'll get this primary one, and all 4 of these methyls are the same. That's one set. And this kind of ties into the NMR thing. How many non-equivalent sets do we have? These 4 methyls are all the same, right? And these 2 methine hydrogens are the same. So for chlorination, I think it's just 2 products. I don't know. Can you see another one? I think it's just those 2. Okay, yeah. Let's see. What about chirality here? Is this a chiral product here? Let's see. Is that a stereocenter? Yeah, that's different. So that is a stereocenter. That would be a mixture of D and L. This one's achiral. That's not a stereocenter. In fact, we should go back here. I'm just thinking about this now. This one's achiral. This one's achiral. Well, what about this one? Yeah, look at that. You got hydrogen, methyl, ethyl, and then chloromethyl there. So that's a stereocenter too, DL. So I'd say total number of isomers for this one, I'd say 1, 2, 3, 4, 5, 6. Just to be thorough there. Yeah, okay. But if we brominate this same substrate here, what do we get? We get out the bromo product there. Okay. And just that one, because that's the more substitute tertiary spot. Okay, here's a multi-step synthesis problem where you're given the reagents over the arrows and you're asked what the final product is. Well, here it's good to think about the intermediate products, right? So if we brominate, we'll get bromocyclohexane, right? And then if we treat that bromide with TB toxide, what do we get there? And remember, that reaction's outside of this range of 12 to 15, those chapters. But this elimination reagent is very useful from chapter, what was that, 8, I think, a long time ago. That will give us an alkene, right? And now here's one of our oxidation reactions from chapter 12, an alkene with metachloroperbenzoic acid. What does that give? Right, the epoxide. So that's a very useful reaction there. And it is just the cis one. You can draw both of these up or both of these down, whatever. It's achiral anyway. But the alkene, we had a couple different oxidation reactions for that we'll review today. And this one gives us epoxide. And that's a pretty neat transformation, I think, an alkane to an epoxide. And then there are other reactions we could do with the epoxide, of course. All right, here's another one from chapter 15, NBS, N-bromosuccinimide with light. So it's radical allylic halogenation. So it's a couple different places we can form the radical. In fact, this problem's a little bit tricky because there's a lot of places we could form the allyl radical here by abstracting that hydrogen, or from here out on the methyl, or from here, I think. This is the only spot we can't take a hydrogen off of, or here. We can't form the radical there. Remember when we form the allylic radical, we're looking at the radical delocalization there. So if we form it out here, you see we can have that resonating with these two localized radicals, right? And that's the stabilization effect there. And then bromine can jump on either one of those. So our first bromination product maybe we can list is this one. Okay, that would be one. And from this one here, we'd have the bromide there. Okay, so there's two. Can you see a couple more? Yeah, we could form the radical here, and that would give us this one. And you might say, well, that would be in resonance down here, but because of the symmetry, the 2-position as a methyl, if we have the bromide here and have the alkene up here, I think that's the same thing. So we got a little bit of symmetry there with that allylic radical right across here. But then if we form this one here, then we have what? The resonance right here, and we could get this one. Let's see. Yep. Looks kind of funny, but we can form that allylic radical, right? And then if we do that, we could trap then with the bromide right there, I think. Yeah. That's a lot. Mixture 1, 2, 3, 4. Okay. And that's like the chlorination of the alkanes. Just list all the products for full credit. Some of these are chiral. Yeah, you'd need to think about DL for a lot of them. This one, this one, that's a stereocenter, that one, and that's a stereocenter too. Yeah. So all of those would be DL. I think all 4 of those. This is the only one here that's achiral. There's no stereocenter there. But again, that's a complicated one. Allylic bromination often gives a mixture, just like alkane chlorination often gives a mixture. But alkane bromination is very selective, or if there's high symmetry within the alkene, then allylic bromination can be selective there. But yeah, okay, that's the first group. Let's get some other problems up here. And you can pause your video if you want, and you can check these out on your own. Not you, Colin. You keep it going, okay? Let's see. So NBS and light on that one. Oh, another multi-step one. And then sodium cyanide. How about this one? HBr. And instead, same substrate here, HBr with peroxide. Okay. And let's see, how about this substrate with that same reagent there? And how about this one with HBr peroxide? And how about this one? Styrene with just peroxide and heat. Okay, see if you can try that. Okay, we're back. So what are you going to get here? Allylic bromination, right? You're going to get a mixture of different things. You're going to get that one. You're going to get this one. And yeah, and this will be a mixture there. This one, you can also get cis and trans there. I'm showing just trans, which is always the major one, but when you trap this allylic radical, this methyl could actually isomerize over on one of the resonance structures. You can get some cis there, but usually it's very minor. If you leave off the cis there from those allylic brominations, you're okay. In fact, let's just say we get this one, we can purify those two apart and then treat with sodium cyanide. What are we going to get? Yeah, we're going to get the cyanide displacement. That's an SN2 reaction, right? Along with the bromide leaving group that we just put in place. All right, this goes way back, and this is helping you review for the final, actually, in chapter 9, right? This is hydrobromination of alkenes, but no peroxide. It's just HBr in there. So what are we going to get? Yeah, we're going to get the Markovnikov product, right? Going to protonate on the end, and then bromide right there. But if we use the peroxide here, what are we going to get? Yeah, we're going to get the anti-Markovnikov product, okay? And that's because peroxide is going to initiate a radical process. The bromine radical is going to add to the end to give the secondary radical, and then that's where the hydrogen atom is going to go on. Same thing with this one. Let's see, we're going to get the less substituted product there. And that's very useful because then we can do a lot of other nucleophilic substitution and stuff from that. So, you know, having these complementary hydrobromination reactions from Markovnikov without the peroxide, right? And then if we add the peroxide, we get the less substitute. Okay, same thing here. So what are we going to get here? We're going to get the less substituted bromine, and that creates two stereocenters. This is going to make it complicated. Cis and trans are going to be there. If you want to show both of them, that's fine. They're both chiral, actually. I think there's 4 total products here. You can draw those out, but make sure you have the bromide there, not there. Okay, if we left out the peroxide, then we get bromide there. But with the peroxide, it's anti-Markovnikov. Let's see, if we leave out the HBr, just use peroxide with an alkene, what are we going to get? Well, here we're going to get the polymerization reaction, remember? So every other carbon here is going to have whatever results on the alkene. So these 2 carbons get polymerized, right? There's 2 there with the benzene on it, 2 there with the benzene, 2 there with the benzene. And let's see, pH, and then, maybe I wanted to have one more on there. There we go. Okay. So there in our polymer, and you can say X there. I'm showing what? 1, 2, 3, 4 monomer units. Okay. So that's giving you the alkene and the polymerization conditions, and you have to come up with the structure of the polymer. So that's good. That's a good thing to look at there. All right. Let's put up some more reactions. We'll get to the sample test here in a second. Let's see, this next group, what can we show here? Okay, alkene with hydrogen and palladium. Alkene, same thing, hydrogen and palladium. Chloro with LAH, we'll have to review what that is. Epoxide with LAH, and we quench with water in that case. And how about this one? Similar type of tetrasubstituted alkene, but osmium tetroxide. And how about an alkyne with ozone? And how about a primary alcohol with H2CrO4? That's chromic acid, remember. And how about an alcohol with that same thing, chromic acid? Okay, work through those. Pause your video if you'd like, and we can help you out with it. And we're back. What do you get with hydrogen? Palladium, you have to have the catalyst in there and an alkene. This is a reduction reaction from chapter 12. Right, we get the alkane. Same thing here. We get the alkane. The two hydrogens add there. Are the two methyl cis or trans to each other? That's the result here. Well, they're going to be cis to each other. Well, why is that? Well, the two hydrogens come in from the same face. Remember, the hydrogen adds to the palladium, and then the palladium hydride actually interacts with this, both alkenes in the same face. Either top or bottom will give you the cis product. Make sure you show cis to get full credit there. LAH is what? Lithium, aluminum with 4 hydrides on it. It's negatively charged. The lithium's positive charge. So you can think of this as H with 2 electrons and a negative charge. Okay, it's not a free hydride, but it's an aluminum hydride. Aluminum with 4 hydrogens on it. Aluminum's the 3rd row over. It's just below boron. So that's 3 valence electrons. Okay, but you have the 4th bond there, so it's negatively charged. So one of these can come off as H minus, right? You can think of that as what? A nucleophile. So here we get the alkane again. Okay. Not really a useful reaction. Alkane's a simpler compound than an alkyl chloride, but it shows the reactivity of LAH. You can see that same reactivity here by popping open the epoxide. So I'm showing a little bit of the mechanism here, just to remind you of what's going on and why we have to quench with water now. That will protonate this alkoxide. It's actually the lithium oxygen salt at that point after the hydride is added. So the water donates a proton, so you draw the electrons like that. And then what's our product? Would be this alcohol, okay, from that epoxide. Okay. How about this one? Osmium tetroxide with a tetrasubstitute alkene. Remember, osmium with alkenes forms what? Diols, dialcohols. So here's our alcohol here. And this one also gets an alcohol. And the 2 methyls get pushed down or up, doesn't matter. Okay, you'll look at it from the top to the bottom, flipping it over. But again, it's the osmium tetroxide lays down on one face, top or bottom, and forms this. There's a hydrolysis step here with water. I told you that part of the mechanism you don't need to worry about, but the cis addition here, the syn addition, the 2 alcohols you do need to show. Okay, and then ozone, O3. This is molecular scissors. So just break this thing right in the middle. And remember, with alkynes, you go to the carboxylic acid. Now, if this was an alkene, right, if we had propene here instead, we'd have what? An aldehyde product. Okay? And we'd also have formaldehyde here, and we'd also have formic acid coming off there. It's the bigger fragment that normally we can characterize. So yeah, this one has a byproduct of formic acid, and this one has a byproduct of formaldehyde. But again, that's just molecular scissors, right? You cut both the pi bond and the sigma bond. Very strong reagent, O3. And then we have chromic acid. This is not H2SO4. This is not sulfuric acid. This is chromic acid. There's a chromium there, and that's a redox active methyl. And look, that's a high amount of oxygen. So you want to think about oxidizing an alcohol, and a primary alcohol will go all the way to what? Carboxylic acid right there. You don't need to know the mechanism of that. I showed you a couple of spots. Some people have been emailing me, what mechanisms do we need to know? My answer is always, know all of them. But I'm pretty clear, I think, in class or office hours, what parts you don't need to know, okay? But you're already seeing some stuff where, yeah, you should be able to handle that. But this one, no, okay? And I was clear there in chapter 12. So don't email me now about this one and say, do we need to know the chromic acid? Somebody will, though, don't worry. No mechanism here, okay? You're off the hook. Okay, I can show you the whole thing, and I showed you part of it just to show you how it worked. If it's a secondary alcohol, this is the key things you need to know. Primary alcohol to carboxylic acid, secondary alcohol to what? Ketone. Now, with this primary alcohol, we could stop at the aldehyde. What reagent do we use to go to the aldehyde? Yeah, it's pyridinium chlorochromate. And I don't have space here to draw that out. But you should know this acronym, PCC, pyridinium chlorochromate, and then be able to draw out the structure. It's similar to chromic acid, but instead of being a strong acid like chromic acid is, PCC's neutral. And that's part of the reason why it stops at the aldehyde. Okay, so a couple of those oxidation reactions you need to know. All right, let's get another group up here, and then we will go to the sample test, don't worry. And we'll be doing that in recitations too tomorrow. The TAs will be going over that. Let's see, how about if we have an alkyne here and treat with hydrogen and palladium, or if we treat with hydrogen and palladium, but the Linlar. And that's letting me off the hook. I don't want to draw out the calcium carbonate, lead acetate, and quinoline over and over again. Linlar, that gets you off the hook there, okay? So same substrate, but with the Linlar catalyst. And then same substrate, but with sodium metal and ammonia. And then alkene here with MCPBA. And how about an alkene here with ozone? And how about this with chromic acid? And this same one with PCC. And let's see, how about this alkene with this set of conditions, plus dextrorotatory diethyl tartrate, DET, maybe you remember this, and titanium tetraisopropoxide and tert-butyl hydrogen peroxide. Okay, there's a bunch of them from chapter 12 that maybe you've forgotten about, but it's good to review these. So if we just take hydrogen with the palladium catalyst, we're not looking at this right now, on an alkyne, what do we get? Right, we get the alkane. We add this twice to both pi bonds. It's hard to control that. If it's just palladium catalyst, that's active enough. And this implies excess. We won't always draw excess there. It's a gas. It's hard to meter out just one equivalent. So that's implied to be excess there. And if you do that, you'll go to the alkane. Now, if we have the poison Linlar catalyst, the first addition, the first pi bond reduction is fast. The second one, because it's all this extra stuff stuck on palladium, makes that next pi bond reduction very slow. So this poisoned or Linlar catalyst stops at what? The alkene. And you see the two hydrogens come from the surface of the palladium from the same side again, and what? You get the cis product. And cis only, okay? Make sure you designate that. If we do it with sodium metal, and this is the shiny stuff, you can draw an electron there if you like. And this is also implied excess. We did go through the mechanism of this and showed you that, how it worked. This gives you the complementary what? Trans product only, okay? So the Birch reduction, or is this the Linlar reduction here? This goes through a radical anion, and then your protonation source is actually ammonia. And then MCPBA with an alkene gives the trans epoxide, okay? Stereoselectively. Ozone here, clip both of those, you'll get a ketone on this side, and you'll get an aldehyde on the other side, okay? So there's right where we broke both the pi bond and the sigma bond. And then chromic acid here with the secondary alcohol goes to the ketone. PCC with a secondary alcohol also does the oxidation. But yeah, look at this. It gives the same product. Okay? Remember, it's only with primary alcohols that we get the aldol. Like with this, if we did the oxidation with PCC here with this primary one, we get the aldehyde here. That is a primary alcohol. But here we're doing the sharpless epoxidation, and if we're doing it with the plus form of diethyl tartrate, we'll get one enantiomeric form of the epoxide, okay, in high enantiomer selectivity. Now, don't worry whether you remember the plus form has it always down or the plus form is always up. You can just draw one or the other. If you drew the opposite enantiomer of this with these both up, we give you full credit. But if you left it undefined, and this is the sharpless thing, we would take off points. So show one enantiomer or the other. Okay, so that's the tartrate, which has two stereocenters. It's a chiral catalyst, we say, and that transfers chirality to the substrate. Okay. Let's see. Yeah, I got a couple more, and then yeah, we will go to the sample test. So hang in there. Let's see. A lot of these are similar problems on the sample test, so it's good to review all these topics here. Let's see. Oh, let's do a spectral one now. So you're given a compound which is C9H12O. Sometimes you have to figure that out from the mass spec and the amount of hydrogens you can see in the proton NMR. But you're given that, and you can see how many degrees of unsaturation you have here. If this is 9, the max would be what, 20? 20 minus 12 divided by 2, so you have 4 units of unsaturation. So that's a lot. Okay, 4 double bonds or rings. Proton NMR looks like this. Let's see, we've got delta 0.9, 3 hydrogens triplet, 1.9, 2 hydrogens quintet, 2.6, 2 hydrogens triplet, 7.2, 3 hydrogens multiplet, 8.1, or 8.0, sorry, 2 hydrogens doublet. Okay. A little bit of IR data, IR 17, 20, and 3000. And the mass spec, molecular ion, 136, sorry, mass to charge ratio. So let's see, what's the structure? That's the tricky part. So this is a line list type problem. We're not showing you the actual spectrum, but you can tell what the integration is here. The shift values are here. That tells you the kind of hydrogens and how many non-equivalent sets. What do you have here? 1, 2. Be careful with multiplets. There might be multiple sets in there. You're kind of lumping them together. And plus coincidental frequencies. You can often have distinct sets right on top of each other. So you have to inspect that, kind of go through it. But some things really stand out here. 0.9 here, triplet, the whole set would be a methyl group with what? 2 neighbors. So you could already see this right here from the multiplicity and the amount of hydrogens. Quintet 2H, that's probably what, a CH2. And then you've got, quintet, you've got what? 4 neighbors? 5 neighbors? How many? 4 neighbors? Okay. Let me change that. Yeah, quintet would be 4. This is showing up as a hextet, I think. Yeah. So that means what? 5 neighbors. Okay. And sometimes that's hard to see. Those little multiplets can be hard to count out. And then this one here, 2.6, so shifted further downfield. So it's going to be next to something. And you've got an oxygen here. So you already see a heteroatom there. And 2 H's, so 2H. And then you've got what? You've got 2 neighbors there. So that would make, these a triplet, right? And then you've got 7.2 multiplet. And that might be hard to see. But the shift region, 7.2 and 8.1, these are aromatic, right? And you've got 5 of them there. So 5 aromatic hydrogens. So you probably have what? Probably have a benzene with just one thing on it. Okay. And this is good because these two hydrogens here, just one away from whatever it's connected to, will be the same set. Okay, and that might be these two here. And then these two are usually the same set, and then this one's distinct. But oftentimes those shifts are right on top of each other, so that can show up as a multiple. So you have to inspect some things here, but I think having the 5 aromatic hydrogens kind of tells you it's monosubstituted benzene. Okay, so yeah, we got some good fragments here, and we've only got 9 carbons. So if this is 6, 7, 8, 9, so you can already see we're already pretty much down there for this. Is it 9 or how many is this? 136? You may have to modify this a little bit. Let's see. Is this 136? If it's C9, what's C9? What's 9 times 12? That's, what, 108? 108 and an oxygen 16. So we're already up to what? 124. And then how many? 12? Okay. 136. Okay. I think we're okay here. What does this tell us here? It's carbonyl, carbon oxygen double bond, and maybe aromatic CH stretch there, along with some stuff. That's pretty much all we can see there. Oxygen, so for a carbonyl, and then you see here these 2 H's right here, alpha to that oxygen, probably these two, and then you've got that multiplet right there, and then the terminal methyl. So yeah, it's probably a propyl ketone here. And then with the aromatic ring here. But something's wrong here. How many carbons do we have now? 1, 2, 3, 4, 6, 7, 8, 9, 10. C10 times 12, that's 120 here. How many hydrogens are showing up in this? 3, 5, 6, 7, 12. Okay, so that should be H12. And then O. So what's that? That's not 136, is it? Am I off here on something? Is this correct here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hydrogens are right. And the signals are right, but I think the mass spec is wrong. Sorry, this should be 148. So yeah, I messed that up. I must have written that down wrong. I'll have to double check. Yeah, so this is a propyl. You see here from the Proton Nmr, these 3 signals here. I think that's true, yeah. And then, yeah, that should be right now. Oh, and this is wrong here to start out with. This should have been 10 to begin with. Sorry about that. Okay, now I think it's correct. Sorry about that. Let's do one more like this, and maybe we'll do a better job. Let's see. And then we will go to the sample test. Don't worry. Let's see. How about this one? 0.9, 9H. There you go. Singlet. 3.2, 2H triplet. 3.4, 2H singlet. 3.7, 2H triplet. Mass spec. We've got 152 and 150. And these are in a ratio yeah, I have to be careful of this. This is 3 to 1 here. So this is actually an M+2 peak. That should tell you something. And we have a lot of stuff here in the 3 range. So we're alpha, we're next door to something here, either oxygen or maybe chlorine, right? 1 to 3 ratio there is kind of telling us what's going on. And the IR, you don't see much. You see 1211, which is a carbon oxygen single bond stretch. and we see 3,000, which is, or less than 3,000, which is CH alkyl stretch going on. So, yeah, what's this? So we can begin to figure this out. This 151 here would be for the chlorine at 35 molecular weight. And if we're at 150 here, you can kind of figure out how many carbons you might have. If you say C8, you see you're already up to 96. 8 times 12, 96. You're already pretty high there. And then if you have, you know, how many hydrogens, you can already count them up here. 11, 13, 14, 15 hydrogens. That's what it looks like from the integration there. So you're already up here pretty high. And if you've got the 35 for the chlorine, you're already up to 1. And then 15 for that, yeah, you're way up there. You're almost to 150, and you don't have any room for the hydrogen. So I think it's C7. And then if you have the 15 hydrogens there, and then the chlorine and an oxygen, I think that gets you to 150. Okay. You can go through that and work that. But, you know, play around with the molecular formula, how many carbons you might have. Sometimes you're given the C13, which can help you out there to count up the carbons. But it's also good to just try to do fragments now. So what's this 9 hydrogen singlet at 0.9? Well, that's a tert-butyl group, right? So tert-butyl, well, there's 4 carbons and 9 hydrogens on it. So that's quite a few already, you can say there. And then alpha here with a triplet. So that's going to be next door to either an oxygen or a chloride. And it's going to have the 2 hydrogens here. But if it's a triplet, it's going to have 2 neighbors there. Okay. So that's going to be something like that. And then here, it's going to mean alpha to some sort of heteroatom. And then something with no neighbors on it. Okay. That's going to be a singlet. Okay. And then same thing here, triplet, that's kind of similar to that piece there. So another heteroatom with 2 hydrogens, and then with 2 here, and then nothing else there. So you kind of see similar fragments there for that. And now let's just link it up. So what could we have? We could have the tert-butyl, and then maybe an oxygen there, which can have a couple things on it. And then maybe, the chloride. How many carbons do we have? 7? 1, 2, 3, 4, 5, 6, 7. Structure like this. Okay, so that would be, triplet here. Oh, but what about this? We have to have something that's a singlet. So this structure may not work. But let's see, if we could put this group maybe over here, what would that do? We have our tert-butyl. And yeah, maybe the methylene right there. Then oxygen. Oh, and then you see we'd have the methylene here. And yeah, that would be a triplet. This would be a triplet. Now it's kind of hard to tell which is which, alpha to chlorine or alpha to oxygen. Oxygen is more electronegative, I think. So it might be this one here for alpha to the oxygen 3%. If you mix those two up, we'd give you full credit. But this one here, you see, is alpha to oxygen, so that's shifted downfield too. And that's the singlet one, 3.4. And no neighbors. This has the quat carbon on it. These are all the same. That's the big singlet, and that one there. There are some other alternatives you can think of here, but this is the best one, I think. You could have the 2 over here, maybe. And then that one. How about that structure? Is that viable? Oh, let's see. Triplet, singlet. Yeah, at least by the multiplicity. But what about by the shifts? Here's 2 electron negative groups, right, next to this. That would make that around 5.5. Okay. So that's too low for the singlet at 3,4. Here the singlet's 3,4, just alpha to 1 electronegative. So that's more consistent. So this one fits the multiplicity pattern, except maybe this, you see this is 1 carbon removed. This should be further upfield. Okay, that'd be around 2.5. But you see both of these triplets are up above 3. So I think this is the correct structure, most consistent with all the data. So there, you got to propose a structure, get to the point where you can do that, and then go back and double check the data. So this is a little bit harder type of problem, but I think you could go through that. Let's look through the sample test now. Colin, let's go back up here and see what we need to go through. I'll just point out a couple things here. Hydrogenation. Palladium catalyst, that's the active one. Which alkene will have the highest heat of hydrogenation? Which one will give off the most heat? This is kind of a tricky one, right, to start off of. You've got all these isomeric alkenes here, disubstituted, cis-trans, and monosubstituted, and then tetrasubstituted. What's the most stable one? Yeah, it's this one here. And if it's most stable, it's lower in its free energy of formation. So it starts out at a lower point. You're asked which will give off the most heat, the highest heat of hydrogenation. So which one would that be? Well, it'd be this one, the less substituted one. The monosubstituted one would be a higher heat of formation to begin with. So when it hydrogenates, it would end up giving up more heat. Primary alcohols, chromic acid, give carboxylic acid. So some of these are just descriptive. NAD plus, we showed how that works as a cofactor to do what? Oxidation reactions in cells. So that's kind of a descriptive thing, but we actually did show you the mechanism of how that works, and it's in the book there. Here's a chapter 15 problem, the allylic bromination. There's 2 allylic resonance forms here, one with a radical here, one there. And those are the 2 products, 1, I think, and 2. You don't form the radical out here. That'd be primary and not resonance stabilized. This one would be on the edge here. That vinyl radical would not be resonance stabilized. It's these 2 right here. So 1 and 2, C is the answer there. Definitions here. Hydride, we just talked about lithium aluminum hydride opening up epoxides. Let's see. See some spectra already there. I think most of those are pretty straightforward. Quartet in the Proton Nmr. Yeah, well, that's the one with 3 neighbors. Okay, the N+1 rule for splitting. There you're not asked about the shifts or anything, just which one would have a quartet. This would be a singlet. This would be a doublet. And this would be a heptet. But this one, because of the 3 neighbors, yeah, quartet. This one's a little bit tricky here. In the Proton NMR, these 2 hydrogens that are indicated have what topicity in the NMR? Well, they're diastereotopic because that's a stereocenter on the epoxide. So that means these 2 hydrogens always have different shifts and they can couple to each other. That'll make things complex in the NMR signal. This one here shouldn't be tricky if you know the shift, and you will have a data sheet with the shift ranges shown there, similar to the scale shown in the outline for chapter 14. The shift table in the book is very similar to what will be on the data sheet, so you don't memorize those shift ranges, but alkyls at 1 ppm, so that's too far upfield. And then aromatics are too far downfield. These would be a 7. Alkenes are at 5. But if you're alpha to an aromatic, yeah, these are benzylic positions. That would be the 2.5 range. Yep. So hexamethylbenzene would have 1 signal. It'd be a singlet. These are all equivalent hydrogens, and it resonates at 2.2. Structure, hybridization, yep. Single electron trigonal planar in a 2p p atomic orbital there. The 2 refers to the level in the periodic table, right? Not that there's 2 of them there. It's just the 2p, the single 2p orbital. Initiation step for alkane chlorination involves homolysis of the chlorine-chlorine bond to create two chlorides there. These we could write out here, giving 4 structural isomers. These are a little bit tricky because you do the monochlorination of each one. You have 1, 2, 3, 4, 5 possible ones for A. Here the 2 ethyls are the same. So these 2 methyls would be the same as 1, 2, 3, 4. Yeah, I think it's B. Yeah. This would be 1, 2, 3 structural isomers. We're not adding up all the stereoisomers. And then this would be 1, 2. Yeah. So that's a little bit tricky. Use your scratch paper on ones like that. Here's the mechanism of allylic radical trapping by BHT, which is butylated hydroxytoluene, which has this structure. 2 tert-butyl groups, and then here an OH group. And that's what we mean by the OH group coming off here. So you have to kind of remember what BHT is to fully answer this question. There's a hydroxyl there, and that's similar to vitamin E that we showed trapping an allylic carbon radical. 2 of these aren't even radicals, okay? B and D you can rule out right away. Here's the radical. Radical-radical coupling, that's very uncommon due to the low probability of having 2 high-energy species next to each other. But here's the regular phenol OH being trapped by donating a hydrogen atom to that radical to give then the alkene back. So it quenches the free radical, we say. That one's a little bit tricky, but look at the book and the discussion in class, and you should see that. Which monomer gives rise to this polymer? Well, this is polypropylene, so it's from propene. Each alternating carbon has a methyl group on it. What about that signal right there? And that's tricky too, because these 2 hydrogens are diastereotopic. So this will be coupled to one of them as a doublet and the other one as a doublet. And it'll show up as, yeah, a doublet of doublets, because these 2 hydrogens are diastereotopic. That's the tricky part about that one. Mechanistic rationale, I think you can figure that out. We've just talked about that. Ozone can undergo radical degradation of chlorofluorocarbons, oxidize alkanes to alkenes. All of these are wrong, okay? Break only the pi bond, not the sigma bond of alkene. No, it breaks both. So the only one that's true here is that, and remember I let you off the hook there. I just told you to read through that. I'm not going to test you on that. So this is an old exam where we did test on what ozone does. It degrades the ozone layer in the upper atmosphere and makes a hole in that position, which mainly hangs out over the South Pole region, which can lead to some damaging UV radiation in that area. It's not a problem now because we don't use fluorochlorocarbons as refrigerants anymore. So let's see, this is a reaction list. I think a lot of these we just covered. Let's see, yeah, we did similar ones to all of these just now. Okay, I think we're all right there. These are a little harder here because it could be more than one step needed. So, and again, this is an all multiple choice exam now, so these can be the choices, right? And the order of the reagents is important. So here you're examining where you end up at. So you need to get an aldehyde here. So you need to do a hydroboration and then oxidation of the primary alcohol to the aldehyde, okay? Here you got to remember what POCL does. It does what? Elimination of alcohols. So I can put your alkene here. And then allylic bromination. Yeah, you get a mixture there, but you could separate that one out from that other one, the minor one, which would have the bromide there and the double bond over there. But that's okay too. Here we're brominating and then eliminating. The more substitute alkene eliminates, that's the Zaitsev rule. And then osmium tetroxide, yeah, the cis diol there. That is the stereocenter right there. So yeah, you'll get a mixture of both of them up or both of them down, okay? You won't get the one where they're trans to each other because that's part of the mechanism here. The alkene lays down on one side of the osmium tetroxide, either top or bottom, to give you either an enantiomer of that. Okay, oxidation of the alcohol that you form after you do the bromination there, yeah. This is a weird looking one, isn't it? Look, cis alkene to a trans alkene. This is a good one to work backwards. How do you form cis alkenes? Well, you do the Lindlar reduction. Well, that came from an alkyne. So how do you get an alkene to an alkyne? Well, first you get the dibromide and then do 2E2 eliminations to get the alkyne right here, right? And then you do the Lindlar poisoned half reduction to get the cis. That one looks strange, but if you go through it carefully, you can figure that one out. Here we're forming an epoxide, opening up the epoxide, and then reducing the alkyne there with the sodium ammonia to give the trans product there. Okay, so here's NMR problems on the exam, the right-on part. But we can convert these over to a multiple choice quite easily, right? So you're told 3 isomeric dichlorides are formed in this type of reaction. You're doing heat and for a given amount of time, and you're going to get dichlorination. Okay, you can get over-halogenation, right? Here's 3 possibilities: the 2,3 dichloro, the 2,2 dichloro, or the 1,1 dichloro. And those have those distinct patterns, right? Here you've got symmetry in the molecule. The 2 methyls are the same, and they have 1 neighbor. So yeah, big doublet. Okay, and then these guys right here, they don't couple to each other. They couple over here. And we're saying multiply it because the quartet doesn't have really good resolution there. So I'm just calling it a multiplet. But that's 2 hydrogens, the 2 that are the same there. Yeah, so that's the isomer that corresponds to that proton spectrum. And then this one here, this is our old friend triplet quartet. That means an ethyl group, right? There it is. And then a singlet here. Yeah, and that's that one with no neighbors. So that's the 2,2 dichloro. And this one, 1,1 dichloro, we have a propyl type thing. And then with this methine, way up at 5.3. Why is this so far deshielded downfield? 5.3, that's alpha to this electronegative group, but there's 2 of them here. Okay, and what's its multiplicity? Well, there's 2 neighbors, so yeah, it shows up as a triplet. Okay, and then the fragments here for the propyl piece, I think you can figure out. So that one there, use your scratch paper, draw out, the isomeric dichlorides. You have to read carefully. We're asking about dichlorides here. So if you draw out a few of them, and there are more than just these 3 that are shown here, but these 3 that are shown are the ones that correspond to that NMR data. Okay. Then we got this one, which you could say, yeah, this looks like a little bit harder one, but again, we just, did one similar on the board, a couple of them, analyzing the fragments. And mass spec, you can see this has an M+2 for bromine. So the 2.8 or the 208 to 210. You can come out with a molecular formula here pretty quick, which is C7H13O2Br. And here you can kind of count up your hydrogens and see, well, you've got this isopropyl thing, 6 hydrogens right here. Okay, and then that. Here we're not giving you, though, the integration, which makes this tricky here. You have to figure that out. And so it's kind of important to go through the molecular formula there. If you come up with C7H13O2Br, you can then begin to see where some things are. This is kind of deceptive too, the C13. You only have the 6 signals here. But again, if you have this isopropyl thing, which you can kind of see, this big doublet here at 1, right? So these 2 carbons on that isopropyl are the same, and that's this larger peak here. That normally you can't integrate C13, so this is kind of an artificial height for these peaks, but you see 1, 2, 3, 4, 5, 6. Actually, there's 2 in this signal, so that's the 7. And then you get to the fragments. You can see an isopropyl. You can see this 2 methylenes next door to each other, the 2 triplets here, like we saw before. So this kind of shows you what those fragments come out to be. And then you just fit them together. And then you have, let's see, oh, the IR, yeah, 1740. So yeah, it's carbonyl. So you can come up with this structure. There are some alternative ones, but if you go back and check your data, you can make all these assignments that yeah, are the right the shifts there. And yeah, we are kind of running out of time. Tune in to recitation tomorrow. We can go through some of these other ones, a couple of harder radical problems. These are harder to do multiple choice, but we could do, those type of things. The worksheets are also there with the solutions. You can see some ozonolysis reactions there and some other similar ones. Here's the sharpless thing again. Oh, here's this cisalkene to a transalkene, kind of using these reagents in another way. And more IR, 13, IR and mass spec, couple ways. Oh, these fragmentations, don't worry about these. I told you I'm downplaying fragmentation. We won't ask you about specific fragments, okay? It's very diagnostic, though. You can learn a lot about your molecule if you do analyze the fragments, but we're not on this test, so you're off the hook there. You can easily tell some of these drugs apart. You can propose a possible structure just from the IR and the mass spec here, because you see the M+2 for the bromine there. And I think that's it. Oh no, here's the one for 14. Some NMR sets of hydrogens, some ones similar that we just worked. This one's a little tricky because of the symmetry. Yeah, the two N-butyl fragments are the same, so you only see 1, 2, 3, 4 sets in the Proton Nmr, but it's the two butyls are the same, right? And then you got this one with the radical stuff. Here's quantifying the isomers, what the expected proportions might be. You can do that from the relative rates and just do a weighted average of those relative rates. I won't have you do that. I kind of discussed, the probability of which one might be more, even though it's less stable. Like if you have a tert-butyl thing here, there's 9 possible hydrogens to remove, right? So you actually see a lot more of that product. But I won't have you do an analysis like this, okay? Here's the auto-oxidation oxygen radical, abstracting a hydrogen atom off the polyunsaturated fats. You can see that one. And then identifying which monomer gave rise to which polymer and thinking about the mechanism. And I think that's it. Sorry, went a little over here. We did review everything. Tune in.